So good afternoon, everyone. I'm Nirmal from Aizar Mohali. So I'm a final year PhD student pursuing PhD under the supervision of Dr. SSP Ramasastry. So today I'm going to discuss about the overview of reagents in organic synthesis. So welcome all of you to the first class of reagents in organic synthesis. So in this class we will discuss about oxidation reaction in organic synthesis and the problem solving class. So first, we'll discuss about the introduction of oxidation and reduction reaction. So, oxidation and reduction reaction is a basic and fundamental and very important reaction in both in organic chemistry and inorganic chemistry. So, in terms of inorganic chemistry, oxidation reaction is nothing but a loss of electron from a starting material to a compound or final product. And in terms of organic chemistry, oxidation reaction is a reaction where attachment of oxygen molecule happened in a final product. In case of reduction in organic chemistry, removal of oxygen from a starting material to a final product is known as reduction of a molecule. Or in terms of inorganic chemistry, reduction is a gain of electron. So if you discuss about the reaction of magnesium metal with molecular oxygen, it is forming magnesium oxide. So in this case, magnesium is zero oxidation state and it is oxidized to +2 oxidation state in magnesium oxide. And in case of molecular oxygen, it is in zero oxidation state and it is forming -2 oxidation state in magnesium oxide. So what is happening is there. So magnesium is losing 2 electron and forming magnesium oxide, whereas oxygen is gaining 2 electron and forming magnesium oxide as a final product. So we can call magnesium as reducing agent as it reduced oxygen to oxide -2 ion and self-oxidized to +2 ion. Whereas oxygen is a oxidizing agent as is oxidized magnesium to magnesium +2 oxidation state and self-reduced to -2 oxidation state. So this is a basic and general overview of oxidation reduction reaction in case of inorganic chemistry. So if we think about the oxidation reaction of organic chemistry, there are several oxidizing reagents which oxidize a chemical reaction and giving final product. So most of them and we studied in our +2 level. So here we had discussed about some chromium-based oxidizing reagent. So first we'll discuss about Collins reagent. So this is nothing but a dipyridine chromium oxide where chromium is +6 oxidation state. And famous and very important oxidizing reagent is a PCC oxidizing reagent, which is pyridium chlorochromate, is very acidic in nature in the case of PDC and PFC, so which are pyridinium dichromate and pyridinium chlorochromate. A harsh oxidizing reagent is Jones reagent, which is chromic acid, which formed by the reaction of uh, chromium oxide and acid such as H2SO4 and H2SO4 HCl. And another oxidizing reagent is Edwards oxidation. This is the reagent where chromyl chloride is used. So we all know the reaction of toluene to benzaldehyde. So it happens through Edwards oxidation. So generally oxidizing reagent is oxidized primary alcohol to aldehyde or acid or secondary alcohol to ketone. So if we discuss about the reactivity between Jones reagent and Collins reagent, Jones reagent is a very harsh reagent. So it oxidizes primary alcohol to acid, whereas Collins reagent is a mild reagent. It oxidizes primary alcohol to aldehyde and secondary alcohol to ketone. So the very important reaction of tertiary alcohol in presence of PCC, which is pyridium chlorochromate, which from alpha beta unsaturated ketone. So if we think about the mechanism of this reaction, so first we'll discuss about the brief introduction of this oxidizing reagent and then we'll go through the question answer session. So if we think about the mechanism of this tertiary alcohol to alpha beta unsaturated enone reaction through PCC. So PCC is pyridinium chlorochromate. So this is the structure of chromate, chlorochromate. So what happened? First, oxygen through its lone pair react with the chromium center, which is +6 in oxidation state, which liberate the Cl minus and generate this oxochromium based compound. Now what happens is there. So this lone pair of oxygen is undergo the reaction of this alkene and which liberate and broke this bond of carbon oxygen, which is then undergo this oxygen chromium based reagent, and after that proton abstraction by the liberated Cl minus as a form of HCl give the alpha beta unsaturated ketone. So as HCl is removing in this system, that's why PCC is slightly acidic in nature. So PCC also prepared from pyridine and HCl. So the liberated HCl is also the reason for acidity of PCC. So this is the final product and this is the mechanism. So if we discuss about the ATAC oxidation, so it's generally oxidized toluene to benzaldehyde. So the mechanism could be, so this is nothing but the in reaction. So we all know chromate chloride structure. So which is chromium is +6 oxidation state, which is this one, and sorry. So if we wait a minute, we write the bond in the bond form. So what happens in reaction? This will go there and this react with the chromium and Cl minus will remove. What happens? This is from double bond, chromium, double bond to Cl. Now this will here, this will go and liberate the chromium. So which this chromium complex, and after the liberation of this proton and chromium give the aldehyde pair. So this is the basic mechanism of ATAD reactions. So now we'll move to the another oxidizing reagents which is activated sulfoxide. So activated sulfoxide has been done by let them- so yeah, I think the screen is visible. So now we'll discuss about the activated of sulfoxide mediated reaction. Basically, discuss about the most important reaction, which is short oxidation. So it generates primary and secondary alcohol to aldehyde or carbonyl. So you all know the mechanism of short oxidation. So DMSO, which is the dimethyl sulfoxide, the structure in presence of oxalyl chloride. So oxalyl chloride is CO. So now it will attack here and liberate the Cl minus. So S plus O minus O C double bond double bond to Cl. Now the liberated Cl minus attack to the sulfur center and generate the activated form of dimethyl sulfoxide, which is S plus methyl Cl. Now the alcohol which we are trying to oxidize react here are OH. So the lone pair of the oxygen will react to the sulfur center and liberate the chlorine. So S methyl oxygen. Now we are using triethylamine as base. So the base can abstract the proton of this methyl from the which generate the negative charge and after abstraction of proton. Now this negative charge abstract proton from here, so this bond will go there and liberate dimethyl sulfide Me2S plus our expected aldehyde or ketone. So these are some example. So where this cyclohexane alcohol is oxidized to aldehyde and this N protected or acetyl alcohol is also oxidized to aldehyde. Now we'll discuss about the one another oxidizing reaction through pan acid such as H2O2 or MCPBA, which is Baeyer-Villiger oxidation. So what happens in Baeyer-Villiger oxidation reaction? When any carbonyl compound uh, rearranged and form ester. So if we think about the mechanism of this reaction, so what happened? R1, this is R. So any acid, I'm talking, if we think about the H2O2, so now the one of the lone pair of oxygen attack to the ketone R1 O minus O OH R2. Now depend on the migratory aptitude of the R1 and R2, the negative charge of the oxide is go there and this R2, a second, someone trying to join. Now we'll discuss about the Baeyer-Villiger oxidation reaction. So the mechanism is this. So depends on the reactivity of R1 and R2. That R2 is R1 and R2. Here I am moving R2 to the oxygen and liberate the which is generate the ester from the ketone. So this is the Baeyer-Villiger oxidation is nothing but a reaction between a carbonyl and a per acid which generate carbonyl to esters. So the migratory aptitude between the groups is 3 degree alkyl group much better migratory than cycloxyl than 2 degree alkyl than benzyl aryl primary and methyl. So if we discuss about the example, so in this case, we are treating with MCPB at sodium bicarbonate. So this is the secondary alkyl group, tertiary alkyl group, and this is the secondary alkyl group. So tertiary alkyl group first migrate and generate this ester here. This is the product forming. And if we discuss about the second example, so this is secondary and alkyl group, and this is primary alkyl group. So here, as the migratory aptitude of secondary alcohol is much better than the primary alkyl, so that's why the secondary alkyl or cyclohexyl migrate and generate this product over the methyl migrated product. Now we'll discuss about the surface epoxidation reaction. Now we'll discuss about the surface epoxidation reaction. So this is the oxidation reaction of allylic double bond to epoxide. So what is allylic position? So this is allylic alcohol, and this position is allylic position. And if we think about this compound, this is vinylic position, vinyl. And if we want carbon is extra, this position is called allylic position. So if we think about the surface epoxidation reaction here, per acid, titanium isopropoxide, and chiral reagents such as diethyl terephthalate or isopropyl terephthalate has been used. So depends on the alkene group. So there are two phase, re phase and C phase. So from the peroxide can come from the re phase, it or can come from the C phase. If it is come from the C phase or the top phase, we will get the OH per acid epoxide, and if it come from the re phase or the down phase, it gives the gas per acid. So this will form the OH like this, and this will form the back side, the gas per acid. So the example of this, the down one. So they are given class deity TBHP, that is tributylcyl hydrogen peroxide and titanium isopropoxide. So it formed the OH epoxide. So how can we explain this? So as they have given the class deity, so first this allylic alcohol we have to change. This is allylic alcohol or not? So this is allylic alcohol. If this is allylic alcohol, so these are the hydrogen. So this is in transform. So first we have to write, we have to rotate it 90-degree angle. So if we rotate it 90-degree angle, this hydrogen come to the left hand and this alcohol come to the right hand. Same as that, this is the transform. So this and this butyl group coming in the left hand. So if the alcohol is right-handed and we are using plus DET, so the epoxide will come from the OH phase, W phase. And if it is left-handed and we are using the plus DET, the epoxide come from the gas phase. So it will be opposite for minus DET, equal minus DET and a right side of the alcohol. So this is from the epoxide form from the gas phase, and it is the minus DET and the alcohol is left-handed. So it will come from the epoxide will come from OH phase. This is the basic understanding. So by this way we can remember this, that if the allylic alcohol is right-handed, the epoxide will come from the OH phase. If plus DET is used or plus diisopropyl tartrate is used, then if the allylic alcohol is left-handed, then it will come from the down phase or gas phase. Then uh, gas epoxide will form or that epoxide will form. So by this slide, I discussed about the overview of the week 1 class. Now we'll solve the week 1 problem which has been given by the NPTEL course. So first, this problem. So the ketone, alpha beta unsaturated ketone has been there, and this is the final product. So the reagent we have to find. So first they have given CH3 MgBr PDC, CH3 MgBr copper iodide PCC, Me2Cu Li PDC, PFC CH2Cl. So first methyl magnesium bromide. So we all know that methyl magnesium bromide is a strong Grignard reagent. So in terms of ketone and enone, the 1,4 addition or 1,2 addition, as methyl magnesium bromide is a strong reagent, strong Grignard reagent, 1,2 addition happen. And in the second option, they have given methyl magnesium bromide, copper iodide. So in presence of methyl magnesium bromide and copper iodide, methyl copper complex will form. So due to this copper reagent, so this is weak or soft nucleophile. Soft nucleophile. But in the case of methyl magnesium bromide, this is hard nucleophile. So in case of alpha beta unsaturated ketone, this position is soft as if we move the double bond, so it can resonate. So due to the resonating structure, this position is soft. Whereas the ketone position is hard. So we all know the SAP principle, SHAP principle, from that soft interaction and harder interaction. So methyl magnesium bromide is hard, so it will react with the hard center of the ketone. So it will form this. With methyl and the double bond remain as such. Now PDC or PCC, if we add in this compound, so same to the last mechanism. This is I'm writing the chromate structure only. Pyridinium chlorochromate, ClO minus. So this or PDC is the pyridinium, this is dichromate. So this will act to the this center, and this double bond will migrate and chlorine is liberated. Which is from this O Cr double bond O minus, this methyl remain as such. Now this oxygen will attack the alkene group and liberated that upper oxygen, will generate OCr double bond O minus methyl, and here the double bond is come. Now this proton is abstract by the Cl minus, which is liberated, and chromium trioxide will remove. So that gives the final product. So the answer is the first option one. So if anyone has any query, they can ask me directly or raise their hand. Now the second question, arrange the following intermediate in the progress of the reaction. So PCC and DCM. Since PCM is dichloromethane, so that is DCM, dichloromethane, DCM. Same as the PCC mechanism. Oxygen lone pair will attract, this will go, and fluorine chloride ion from the same as the OCr double bond O double bond O bromine. Now as PCC is slightly acidic, so this the liberated Cl minus will abstract this proton, and the chromium will remove, and from the aldehyde from the alcohol. So this is geraniol. Geraniol is the structure is geraniol actually. So it will form this from geraniol, neal to geraniol, and then in the acidic PCC condition it is protonated, and this double bond is, as it is electron rich double bond due to the both methyl group. So this double bond is highly electron rich, so it will attack that aldehyde due to the acidic nature of PCC. Then it will form the six-member ring, and this carbocation, and after elimination of proton, this carbocation finally gives this product. So from this you all know the order of the reaction. Now we'll discuss about the next problem. So find out the product in the following reaction. So PCC, aldehyde, alcohol, both are there. So which product form? First, what happens is there, if we write this way, as PCC is acidic in nature, so this carbonyl is protonated, and the lone pair of the oxygen will attack here, and this is from oxygen OH. Now This the secondary alcohol is convert to ketone in presence of PCC partner and for this product. The next question is to find out the product in the following reaction. So they have used BMSO oxalate chloride. So this is Swan oxidation condition. There are two alcohol, this and this. So this is geminal alcohol, which is sorry, this is vicinal alcohol, which is closest. And between this alcohol, sorry, the first alcohol, I'm writing like this. Alcohol one and this one, the down one, and okay, alcohol two. So between these two, the upper one is more hindered due to the this bridged ring system. So this alcohol is in the down phase. If we think about the cyclohexane form, so both the alcohol is the down phase. And among this is the bridge system. So for the swan oxidation, so this alcohol and this alcohol has to react. So it is more free. If you compare about this and this, the alcohol one and alcohol two. So if we think about the chair form, the alcohol one is very hindered, so that bridge oxygen is upside. So at this alcohol is downside or the backside, and this alcohol is more free. The alcohol two is more free in chair form. So that's why, due to the hindrance reason, this alcohol is oxidized in the strong oxidation condition, but and this alcohol one remain as such due to the hindrance. So and you can think also the quaternary center. This is the quaternary center of this alcohol one. So this is the reason of that. The second option is the right option. So now next question is to find out a suitable reagent for the following transportation. So Collins reagent is a very mild reagent. It can over oxidize primary alcohol to acid, primary alcohol to oxidize to aldehyde in Collins reagents. Mopel's oxidation also, Swan oxidation also, primary alcohol oxidized to say, aldehyde. But in case of Jones oxidizing agent, so Jones oxidizing agent ki, what is Jones oxidizing agent? It is chromic acid. The structure is H2Cr O4. This is the structure of Jones of uh, reagent chromic acid. So how it is formed? It is formed by the reaction of chromium trioxide and H2SO4. So chromium trioxide is what happens is that due to the acidic nature of H2SO4, this oxygen is protonated, and as H2SO4 is aqueous in nature, so we use aqueous H2SO4. not the concentrated one. So there will be water. So that react with the chromium center from this. This generate CrO, OH, that is chromium H2CrO4, chromic acid, plus 6 oxidation state. So this is very harsh as H2 support is there. So that's why it's directly convert aldehyde to acid. So first primary alcohol oxidized to aldehyde, and that aldehyde is directly convert to acid by the harsh oxidizing reagent. So the right answer will be Jones oxidation. Next, okay. Find out the product A and B respectively in the following reaction. So acid is used. So in presence of ketone and acid, their bilateral oxidation happen. So we have two type of ketone are there. One is O-methoxy in para position of benzene ring. One is nitro in para position of benzene ring. So methoxy is electron donating reagent as it has lone pair. So the lone pair will come to the benzene ring. So it has electron donating property. Electron donating group methoxy. Whereas nitro is a electron withdrawing property. So it takes the electron from the benzene ring. So electron withdrawing group. So we all know the mechanism of bare bilateral oxidation. So if I write this way, R1, R2, in presence of R acid, I am writing H2O2 as a R acid, hydrogen peroxide. So first, what happened? That H2O2 will react on the carbonyl center. It is from O minus OOH and R2. So now, when this negative charge of the oxygen is come, one of the two R1 and R2 has to move to the oxygen center to liberate alkoxide. So which one is moved? The magnetic activity depends on the electronic effect of the group. So the alkyl group or aryl group which is electronically more will first migratory aptitude is highest, whereas the alkyl and aryl group the electron donating property is less migrate. So in between these two, methoxy and nitro, the electron donating property of methoxy is much more, so it will migrate fast. The migratory aptitude will be highest for methoxy containing compound than nitro containing compound. So the right answer will be first in this case the product which is formed is BCO this aryl OMe which is margate because this is more electronically rich due to the electron donating effect of the methoxy group. So that will migrate. Now, if we think about the electron withdrawing effect of the nitro group, so um, so benzene ring are there and benzene ring with substituted para position at nitro. So it is electron withdrawing group. So between benzene and para-nitrobenzene, benzene is more electronically rich as it has no electron withdrawing group or it is neutral, you can say. But in case of nitro, it is more electronically uh, less electron electron is less there for migration purpose. So between this nitrobenzene and benzene, benzene will migrate first than nitrobenzene due to the electronic effect, as benzene has high electron density than the nitrobenzene. So this is the product which is formed is benzene will migrate, so it will form this one. So the right answer will be the last one. Now coming to the next question, find out a suitable class deity for the first reaction and product with stereochemistry. So first we discuss about the stereochemistry. So this is the allylic alcohol. This is the left-handed. So if use plus deity and minus deity. So the right-handed in presence of plus deity will go to OH phase, and in presence of minus both come from the gas phase or down phase. But in case of minus dt, the right one will come from the down phase and the left one will come from the OH phase. So it is in left. So left, the plus dt will give the down one product and minus dt will give the OH one product. So let's find minus dt minus dt OH minus dt OH plus dt plus. Okay. Now between these two products, the first reactability we have to check. So the B and C is the correct answer among the stereochemistry. So now we have to check the first reactivity. Which one will be the first? So that depends on the quaternary this methyl group which is present here. This and this. So as it is in the upside, so the reaction, the uh, the methyl is wedge. Methyl is in wedge form. So the parasite which is coming from the wedge phase is will form steric hindrance due to the methyl wedge form. So it has to come from the down phase to avoid the steric hindrance. So as this methyl is the wedge phase or up phase or front phase, so the parasite has to come from the down phase to avoid steric hindrance of this methyl group. So now between B and C, C will be the right answer because this is the down phase and this methyl is coming from the wedge phase. So this is the right answer. So if you have any queries, you can ask me directly or raise your hand. So I guess this is fine for everyone. So the reason is the steric hindrance. Now the next question is find out the possible condition in the following transformation. Aldehyde, this the cyclopentene alcohol is there. So COCl hold to DMSO, oxylyl, sorry, oxylyl chloride, DMSO, DCM, oxylyl chloride, DMSO, DCM minus 78 degrees centigrade. So ask, try to draw the mechanism of short oxidation. It's basically short oxidation condition. Oxylyl chloride, this is CO. So now the oxygen attack on the carbonyl center is divided the Cl minus. So methyl is plus O P double bond O. Now the liberated Cl minus attack on the sulfur center and remove break the SO bond, sulfur oxygen bond, which is forming, I'm writing here, methyl is Cl methyl plus. Now the alcohol lacking ROH, this will come and the leaving group Cl minus will liberate. So this will give methyl plus oxygen. R CH3 sulfur SS positive oxidation state. Now in solid oxidation condition we have to use base. So base will extract this proton and generate this negative charge. This negative charge will extract this proton. This will go and it will liberate dimethyl sulfide. Ma2S plus R aldehyde. But in absence of base, if there is no base in the reaction, what happens? What happens here? Methyl SOR plus methyl. So in case of base, that will extract this proton and liberate dimethyl sulfoxide, leading to the formation of aldehyde product plus dimethyl sulfide. Dimethyl sulfide. But if there is no base, then what happens? The liberated chlorine chloride ion, which liberated first from the auxiliary chloride reaction react with this R group and remove this DMSO which form RCl plus dimethyl sulfoxide back. It can be used as a catalytic amount and is regenerated after the reaction. So the answer will be for oxidizing agent base is required. For the nucleophilic substitution reaction by the chloride ion, base is not required. So the first option is the right answer. Now we'll move to the next question. This is the final of the product in the following reaction. P16 benzotriazole 2 to 3 degrees centigrade BCM. So there are two type of alcohol. One is the secondary alcohol. One is the what type of alcohol is this? Allylic alcohol. Just like that, Sharpless epoxidation reaction. So it happens in the allylic alcohol case. So between these two, this alcohol is very much activated. Why? Why this is activated? Because of this double bond, lone pair of this oxygen undergo resonate, lone pair of the oxygen participate in this resonating structure of this allylic position. So if we write this way, so this will form the resonating structure like this oxygen mass. So this is very labile. So between if we use one equivalent of PCC, one equivalent of PCC, so it first oxidize the allylic double bond, so which is electronically biased. Biased means if this electron is continuously circling between the allylic double bond and oxygen lone pair, oxygen. Uh, that's why it's very labile. But in this case, the lone pair of the oxygen or electron density is fixed there. Here electron density is continuously moving in case of allylic position, but in case of secondary alcohol, electron density is fixed there. So that's why this is very labile. So if we use one equivalent of PCC, the allylic alcohol is first oxidized, then the secondary alcohol. As both the alcohol is secondary alcohol, this is also secondary alcohol, but this is allylic alcohol due to the allylic double bond. So this is more labile. So that's why PCC first oxidize this one, then the other alcohol. If we use two equivalent of PCC, two equivalent of PCC, then both the double bond will, both the alcohol will oxidized. But this carbon is not tertiary carbon, or this alcohol is not tertiary alcohol, so this option is not happening. The movement of this allylic alcohol to this is not happening in this case. So I think this answer is satisfactory for everyone. Now we'll move to the next question. So next question is this. This is from the Bayer vinegar oxidation reaction. So ketone in presence of MCPPA, BCC, DIPT, H2. So DIPT, TBHP, diisopropyl titanium isopropoxide is used for surplus oxidation. It will not use here for rearrangement of this ketone to ester. DCC DMSO is also as oxidizing agent of alcohol to ketone or aldehyde. H2 is normal water, so it not will affect here. Yes. So now we draw the mechanism. So first, metachlorocarbenzoic acid. The structure of metachlorocarbenzoic acid is this one. Benzene ring, meta position as oh, metachlorocarbenzoic acid. Chlorobook is there. And this acid with part two oxygen is there connected. That's why it's called PAR acid. Now what happens is there the PAR acid will attack from the ketone and the ketone electron density move to the oxygen. Minus C double one two and this benzene it two. Now when this oxide negative charge move to the benzene ring side or the four membered butane side, cyclobutane side. So now there is a possibility of the migration of this single bond or this single bond. So which one is migrate? So if we compare the reactivity or electron density, so chlorine is a electron withdrawing group. So the electronegativity is very good in case of chlorine. So first chlorine electronegativity is highest, then chlorine. So it abstract the electron density from this single bond. So this is the electron density of this single bond is less. But in case of this, there is no such. So, but in this case, the electron density is more than as this is partial alkyl group. So it moved fast than that this double bond, this single bond. So the migratory aptitude is better for this double bond than this single bond than the chloride ion added single bond. So the structure which is formed is this one. So the right answer will be NCTBA, sodium bicarbonate, PCA. So we can also discuss the with 0 plus. The first question is the oxidation number of hydrogen is plus 1. Always. So this is not true. The reagent, so in case of methyl hydride, such as sodium hydride, potassium hydride, in that case, oxidation number of hydrogen is minus 1. In non-metal cases, plus 1 oxidation state is right, but in case of metal-based compound, the oxidation state is minus 1, such as sodium iodide and potassium iodide. The algebraic sum of all the oxidation number in a compound is 0. So this is also true because in all the cases, the algebraic sum of all the oxidation number is 0, such as in K2CR2O7. If we discuss about K2CR2O7, so potassium is plus 1 oxidation state, so this will be plus 2. Chromium is plus 6 oxidation state, plus 6 into 2 plus oxygen is minus 2 oxidation state, so 7 into minus 2. So this will be 2 plus 12 minus 14. This is 14 minus 14 equal to 0. The so this is right. The algebraic sum of all oxidation number in compound is 0. An element in the free or combined state bears oxidation number 0. An element in the free or combined state, free state it can be 0, in combined state also. So this is also true. In all its compound, the oxidation number of chlorine is -1. Yes, but it is always electronegative. H such as H H plus H minus. Which of the following arrangements represents increasing oxidation number of the central atom? So CrO2 we have to calculate. CrO2 2 minus must be like the CrO2 2 minus then ClO3 minus ClO3 minus CrO4 2 minus CrO4 2 minus MnO4 minus. So calculate the chromium oxidation state. So X plus oxygen is -2 into 2 equal to -2. So X equal to -2 plus 2 equal to 2. So here chromium is +2 oxidation state. In this case, X plus -3 into -2 into 3 equal to minus. Sorry, this is chlorine or chlorine. So this will be x equal and -1. X equal to -1 plus 6 equal to +1. And this is chromium x -4 into -2 square equal to -2. X equal to 6. Here it is 6. There it is 5. Even over minus x -8 equal to -2 -1, sorry. So x equal to 7. Yeah, this is 7. So the oxidation state of MnO4 greater than chromium 2 minus, greater than chromium 3 minus, greater than chromium 2 minus. So the right answer is the last one. MnO4 minus, CrO2 2 minus, CrO3 3 minus, CrO4 2 minus. So find a suitable reagent for the following transformation. So this is the alpha beta unsaturated ketone. So this is the oxidizing reagent. So this will not happen. Lithium aluminum hydride is reducing agent, but it's very strong reducing agent. So it can reduce double bond also. So this is also wrong. Hydrogen tellurium is a hydrogenation reagent. So this hydrogenate alkene to alkane. So this is also not happening. So sodium liquid ammonia could be the right answer because sodium is a single electron donor reagent. So through the single electron transfer, it reduced carbonyl to alcohol. And next one question is find the suitable reagent for this following transformation. So KMnO4 is highly oxidizing agent. So it oxidizes alcohol to acid. So it could not be the right answer. COCl hold to DMSO triethylamine. This is the strong oxidation condition. So this can be oxidized alcohol, primary alcohol to aldehyde. So these are the reducing agent, BH3, red al. These are all reducing agents. So this would not be the right answer. So first right answer will be for oxidizing condition reaction oxide chloride DMS and triethylamine. So BH3 THC find out the product of the following reaction. So BH3 THF is a reducing agent which generally reduce acid to alcohol, primary alcohol. So the right answer will be that D. So you can learn about that BH3 THF. So it is reduce acid to alcohol. This is the week 0 assignment which I have solved. Week 1 assignment also I have solved. So this was the week 1 assignment. And we have also discussed about the introduction of oxidation reduction in organic chemistry and inorganic chemistry. Oxidation reagent by chromium, Collins reagent, PCC, PDC, PFC, Jones reagent, Etar's oxidation. So these are the important reactions which I have discussed. The tertiary alcohol can be oxidized to in alpha beta unsaturated ketone through PCC oxidation. Primary alcohol oxidized to acid in presence of Jones reagent, but in aldehyde in presence of Collins reagent. So this is the ETARS reagent which chromium chloride which oxidize uh, toluene to benzaldehyde. Next we discuss about the Swan-Swisson condition, primary and secondary alcohol converted to carbonyl. So the mechanism and example we have discussed. We have also discussed the Baeyer-Villiger oxidation condition for carbonyl oxidized to ester in presence of hard acids such as H2O2, hydrogen peroxide, or metachlorocarbenzoic acid, which is commonly used in Baeyer-Villiger oxidation condition. So we have also discussed about the migratory aptitude. So 3-degree alkyl group is much more faster migratory aptitude than the secondary and primary because of the Plaza effect. So 3-degree alkyl has highest Plaza induction. So that's why the electron density is much more there. So it must migrate than the other. So also the aryl group which has electron donating component of the aryl backbone migrate fast than the electron withdrawing component because of the electron density of that group. So these are the surplus oxidation so which we have discussed. So the how we can assign the stereochemistry of the arylic alcohol we have also discussed. So the how the OH and gas oxidation happen. This is we have discussed. Then we start the previous week 1 question answer which explanation and mechanism. Also we have discussed about the week 0 assignment. So that's all for today. Thank you for your cooperation. See you in the next class in the next week. Thank you, dear. If you have any question, you can ask me or raise your hand. Then I will close the session. Okay, then bye bye. Thank you for your kind attention.